You can bring the homework to the front and okay, so there are a few questions being asked through emails and also Moodle. So there are a few things. I mean, I have some stuff that I think I should talk about with regarding the material that we covered. So yeah, so first of all, let me just do it using a whiteboard for today. Okay. So first of all, because some of you took a closer look at the front page of the exam, so you notice that there's this new distribution that we never talked about, but I sent a Moodle post yesterday, but I just want to talk about it really quick. The multinomial. Okay, so multinomial distribution by the name, you might figure that it is very similar to binomial, but now you not only have two outcomes, so for binomial, you have two outcomes. And P is the parameter, which measures the probability of success. Okay? So multinomial is you have more than two outcomes, more than two, so you cannot have two, so it's larger than two. And the parameters associated with that. So usually you see like in the notation that I provided, it is P1, P2, until Pk, where K is the number of outcomes, okay? So you notice that if we start writing that, you will see the random variable now is becoming a vector. It's not just one number anymore. So for the binomial, you're counting the number of success, and that's the random variable, right? So back here, you have binomial with n, which is the total number of trials that you do, and then p is the only parameter, okay? However, once you move to multinomial, you can think of it as y1 until yk, okay? Now it's a whole vector following this multinomial distribution. So few points over here. So first of all of the sum, sum of all of the, let's see, I from 1 to k is 1. Okay, just like binomial, if you have success probability to be p, then failure probability is 1 minus p. Okay, but with multinomial, I have more than 2, so, but they still sum up to 1. Okay, and the second one is, so here, sometimes we also have one more n in this multinomial density, and that n is the total number of trials that you're doing. So for a multinomial random variable, so each of the yi is telling you how many objects are in one particular category, right? So y1 gives you the number of objects in the first category, et cetera, et cetera. So another restriction of all of the outcomes over here will be y1 plus y2 plus until yk. They sum up to bn. That's the number of trials that you're doing. Okay, so in the binomial case, it's y and n minus y, right? Because it's y number of success, so that will be n minus y number of failures. For the multinomial, you can think of, okay, let's maybe look at a more concrete example. So now let's say we're looking at the distribution of people's responses to their race category, for example. Say there are 5 categories over there. And then if I ask like 100 people to respond to these questions, then y1, y2, y3, y4, y5 are the counts in each of the category of the race choice, okay? But you notice that because I asked for 100 people, so the sum of the number of counts in each of the categories should sum up to 100. So that's what that restriction is. And then also here, P1, P2 until P5, that gives you the probability of a person falling into that particular category. And then they sum up to 1 because you assume that in your sample space, that's the only 5 choices that you have. Okay, all right, yeah. So right, because some of you asked about this, and I feel it's fair. It's fairer if I talk about this in class, so everybody knows what it is. Okay, but on the front sheet, you notice that I give you all of the commonly used, including the multinomial. I give you the density, and then yeah, so it's just there, and then so you don't have to prepare those in your cheat sheet. And since the density is given to you, so you can imagine that no matter what kind of distribution it is, if I know the density, I can write out the likelihood. If that's the data model, I can write out the prior if that's the prior, et cetera, et cetera. Okay, so you should, yeah, so that's just like a background over there. Okay, all right, so this is the first one. And then the second one is, okay, so I got a question through email. I just read the question out loud and then we can talk about it together. I'm confused about when to use the predictive posterior distribution. I recall in lab 2, we did Monte Carlo sampling approximation to sample from the posterior and the data, but then we also sampled from the predictive posterior. I know we would do the former if we don't know the exact predictive posterior distribution. Aside from this situation, what is the main difference / benefit between the two methods? Okay. So let me just bring this up again. So Monte Carlo, again, right after this, I will post the solutions to homework 3, so that will be relevant as well, especially for the take home. So Monte Carlo approximation. The question is talking about for predictive distribution. So predictive distributions. So I will talk about lab 2 and then also homework 3, maybe all together to address this particular issue. So lab 2, what we did, okay, sorry, let me start with homework 3. Maybe that's easier because you just did it and then you will see a clearer context over here. So for homework 3, there are 2 questions, and let me break them into 3 parts. So 4.2, part A and part B, this are talking about posterior distribution of the parameter. Okay, and then the third part of 4.2 is part C. That's talking about posterior predictive. That's when you start to generate new data. Okay, you're trying to generate new data. So that's question 2, part C. And then question 3, which is 4.3, they have both A and B, but both of this is talking about posterior predictive checks. Okay, yeah. So in Monte Carlo approximation, we talked about 3. Oh yeah, sorry. Right. Okay, so in Monte Carlo approximation, we in general talk about 3 different things. Okay, so the first one is just about how you like generations of posterior distribution, say like in the beta binomial, gamma Poisson. When you're just doing posterior of the parameter, you stopped at just the posterior of the parameter itself, right? Yeah, so if you know what the distribution is, we're saying that, okay, you can actually use Monte Carlo approximation to sample independent samples from it and then summarize from there. So if you know the exact already, probably doesn't make too much sense to do the Monte Carlo approximation. But the example that we have seen, especially in homework 3, 4.2, they actually ask you to simulate, say, bunch of theta A and bunch of theta B, and then compare them. So in class, we also talk about if you know the exact distribution posterior of 2, but if you want to learn about their differences or their sum or their ratio, et cetera, then it's very hard to derive the analytic solution of that. So you should try the Monte Carlo approximation. Okay, so that's the general framework. But overall, what we have seen so far is you still know exactly what the distribution is. You just don't know like the relationship of 2 of them, or 3 of them, or many of them. So you might want to do Monte Carlo approximation, because if you have independent draws, if the number of samples is large enough, you're gonna have very good approximation to the analytic solution. Okay, so that's the background, what we did before. And then 4.2 part C is asking you to, okay, replace, like the question is saying that replacing the event of theta b less than theta a with the event of y tilde b less than y tilde a. So once you see like y tilde or like y star, people use different notations, but I would state very clearly which one, like what is what, but usually people have these 2 different notations for posterior predicted distributions, meaning that you're generating new data. Okay, so what we talked about in class as well as in the homework is, okay, now if I want to see how my prediction can work, I want to make a new prediction or a set of predictions for the future outcomes, then you will do the posterior predictive, and the way that we talked about how you can do it is related to lab 2. Okay, so let me just, okay. So lab 2, we talked about 2 ways of doing that. Okay, the first way is, okay, so I will use the gamma, Poisson gamma as the example, because that's what we use in lab 2. So the first way to do it will be, okay, I sample all of my theta from the gamma posterior, and I use upscript S over there, and S is from 1 to capital S. So this is the posterior. Okay. And then because I have all, like a lot of samples of the posterior, I can also just sample directly from the data model to get the new data. So I will use y tilde over here, and then that will be given this particular S. And in this case, because the data model is Poisson, so I'm gonna generate from there. And this is the most common way that we use, okay? And in lab 2, we also talked about, okay, so the goal of lab 2, just to like elaborate again, the goal of lab 2 is, for the gamma Poisson gamma case, you will notice that if you try to derive the posterior predictive distribution of y, you will notice that it's gonna be a negative binomial, okay? So this is the case that you can actually derive the analytic solution of y star given y, or y bar given y, okay? So back then, I was saying, okay, in lab 2, how about you also verify just directly to generate it from the derived analytic solution of negative binomial, okay? So you know what the distribution is, you know the hyperparameters, so you can generate a bunch of y tilde over there, okay? And again, S is from 1 to capital S, okay? So back then, for this lab 2, I was trying to ask you to verify, okay, 2 approaches in general. If I don't know the analytic solution, I can still do it step by step. If I do know, then I can generate directly from the analytic solution, which is negative binomial over here. So the goal of lab 2 is ask you to verify. So first of all, practice how you can generate samples in multiple contexts, as well as to see, okay, whether this 2 approach give you similar results or like pretty much identical results. So as a verification or justification as, okay, even though you know the analytic solution here, you don't even have to worry about the analytic solution. You can just go with the usual way that we talked about. And in many other cases, give me a second, many other cases, the analytic solution is not available. So don't even bother thinking about that. Just go with the posterior and then sample the new data from the data model. Yes, Eli?
It seems to suggest what looks to me like a sort of third primitive. Is that you sample data along with the S from the posterior, and then it says approximate the probability of y tilde condition on y with the sum of 1 S of the y tilde condition on data divided by S. What is, I'm struggling a little bit to understand how that procedure entails and how it relates to what we just talked about.
Okay, so Eli's point, okay, let me read this for those. Okay, so it's on page 61 if you brought the book with you, and it's in the middle. Okay, so the middle paragraph, and then start from 1, 2, 3, 4, 5, the 6th paragraph. Oh, sorry, the 6th line. To obtain the posterior predictive probability that y tilde is equal to some specific value y tilde, we could just apply the multi-column method of the previous section, sample theta 1 until theta s from IID, the posterior, and then approximate y tilde given y1 to yn with the sum of all of the y tilde given theta s from 1 to capital S and then divided by s. So that one is actually talking about how to get the posterior mean, posterior predictive mean. So it's not something new. Yeah. So if you read it carefully, they are saying that to obtain the posterior predictive probability that y tilde, maybe I shouldn't say the mean. It's asking to get the posterior predictive probability that y tilde equals to some y tilde. Sorry, capital Y tilde equals to some y tilde. Then you're using multicolor approximation. So the general, like the key over here is if you sample enough sample size, and then you'll be able to approximate that particular probability. Yeah, but in practice, what we usually do is you sample the posterior first, and then you sample the predictive from the sampling model, like the sample model or the data model. And then over there, so up there, I think the point that you talked about is more like a mathematical justification of why that works. Okay. But in practice, we do either number 1 here or number 2, and most commonly is number 1. Yes?
So you say that if you don't have the posterior distribution, then you should use the distribution, the predictive distribution. But to derive the distribution, I thought you needed to know the posterior.
Yeah, sorry. I mean, if you don't know, okay, so this is the posterior predictive distribution. So say beta binomial in class, beta binomial beta in class, we realize it's another binomial or Bernoulli for a particular one draw. And then gamma Poisson gamma, it's a negative binomial. But then for many other cases, which we haven't talked about yet, but in other cases, you might not be able to derive what this distribution will be, which is the posterior predictive distribution. If you don't know that, then, but you still want to generate new data, then I was saying, if you know the posterior of the parameter already, then you can generate from that and then generate the new data from the data model. Yeah. So in any case, you still know what the posterior distribution is. Okay. Anything else with like about this predictive, I mean, multicolor approximation and then predictive distribution in general? Yeah, so to answer that particular question, I guess the main difference is like in order to, so between these two, you can do number 1 in any kind of situation. Okay? You can only do number 2 if you know what the posterior predictive distribution is, and that requires you to have derived it here and there in some way. Okay, so but then if both are available, especially if the second is available, because 1 is always available right now, at least what we have talked about so far, then if both of them are available, if you do both, just like in lab 2, you will come to the same results. And that's what lab 2 is about. Okay? Okay, yeah, so I will post the solutions to homework 3 right after class today, so you can take a look. And right, I mean, again, I think that solution is probably most relevant to the take home. Okay, but still, if you have any questions, say about that, I mean, at 6 when we're gonna start the midterm, I will be available. You can just ask me really quick before you take the exam if you have concerns about that. Okay. All right. Okay, there's this, and then one more thing I want to talk about is some of you stayed after class last time to ask about this particular. Oh, let me show it. I actually have it over here. For the 1 parameter model case. Give me a second. I somehow, give me a second. Okay, somehow it's, never mind. Cannot connect to my Dropbox at the moment, so I can just write about it. Never mind. Okay, so I was talking about, I'm hoping to talk about the kappa 0 that some of you asked about. So let me bring it back. So it's the one parameter model case with the normal. So what we have is, let's see, y, okay, y1, y1, or yn. This is the data model. We use theta and sigma square, okay? Sigma square known. And then in the one parameter case, we put one extra layer over here. We assume the prior of theta is another normal with mu 0 and tau 0 square. Okay, so this is the setup. Okay, so last time we talked about how to derive the posterior, and in particular how to understand what the posterior is telling us about. So let's write it over here. It's a rather complicated formula over there, so I will use some of the placeholder here for now. But I want to talk about the mean in particular, because some of you stayed after class to ask about how can you think of kappa 0 as the prior observations of the same sample or similar population. So let me just rewrite that part for you and then describe it. So what we have is, if you try to express what the, okay, so everything start with this. If you derive it and then use the notation that you have from before, you will come to something like this. All right, so tau 0 squared, this is the prior variance of the mean, okay, which is the normal, it's the variance from the normal. So we talked about this being the variance, so this will be the precision, right? So that's what we talked about last time. And of course, you have the sample precision as well as the posterior precision. So here, if you start thinking in terms of precision, you see that this is the precision over here from the prior. This is the precision from the data, and then this is the sum of the precision. Okay? So last time we were talking about, okay, let's actually rewrite it in some other way to understand it. And in particular, we're going to define, let me just write it first. Let's define a kappa 0, which is in this way. Okay? And let's use this, and then we will be able to express the posterior mean into a simpler form. And no matter which form that you use, the general story is the posterior mean is a weighted average. So these are the weights, and these are the prior mean and the sample mean. Okay? So even if you're writing this way, as you can see, like you say this is A1, A2, and then this, like the weight for mu 0 will be A1 over A1 plus A2. Right? So in which way, no matter which way you look at it, it's going to be whatever. So the question back then is, how come you can decide to come up with this kappa 0 all of a sudden and define this to be the number of prior observations from the same population as Y1 to YN. Okay? So what we were talking about last time is you're going to assume, so this is the data, Y1 until YN, okay? And we assume that it is IID from this, okay? And we say that kappa 0 is the prior sample size. So I think back then the concern is, how come I know that if I set up my kappa 0 in this way, in particular in this formula, that it's going to represent my belief, say, like the number of prior observations over there. So just to give some background over here. So if you think about kappa 0, and we're saying that we assume this will be the number of prior observations from the same population as Y1 to YN. But think about the prior is on the mean. Okay, the prior is on the mean. So if you think about, okay, case, because now we're assuming that the prior observations are from a population that is similar to what we have seen so far, y1 to yn. But don't forget, the prior is on the mean of it. So by central limit theorem, you know that if you have y1 to yn is iid, theta sigma squared, then if you think about the mean, it's going to be y bar, for example. It's going to be normal, let's see, over n, right? By central limit theorem, the mean of the observation will follow center, like follow a normal distribution, center at the mean, and then this is the standard error, which is sigma divided by the sample size. Okay, so that's why the kappa goes under sigma square, because tau zero is the variance for the normal of the prior mean. Let me say that again. So we're assuming kappa zero to be the prior sample size, okay? And we define it to be tau zero squared equals to sigma squared divided by kappa squared, or kappa zero. And kappa zero, since it's a sample size, and in particular, kappa zero is about the prior sample size, and the prior is on the mean of the observations. So if I have y1 until yn to be the sample that I have, and I want to have equivalent, whatever out there, to the sample itself, but I'm working with sample mean, so I should think about what y bar should follow. So by central limit theorem, it's going to be center as like theta, and then sigma squared over n. Okay, so this n is the sample size, and now I'm trying to think about how many prior observations I should have. So kappa zero is the prior sample size. So the relationship, so if you look at this relationship over here, so this is the data, and this is the prior on the mean, right? If I want to have the mean here to be from the same population as the data, then I'm working with the mean itself. And the mean, if you think about, if I want to have the equivalent, I should think about central limit theorem, because the variance is not sigma squared anymore. It should be sigma squared divided by n. And here, n is kappa zero. So that's why I should set my tau zero square to be sigma squared divided by kappa zero, if I try to define kappa zero to be the prior sample size, as how many prior observations that I can have. Okay, so I mean, this is pretty subtle, and I think actually like I didn't pay too much attention when I was preparing like the first time, and then some of you asked the question, and then I went back to think about it. And I think the real reason behind this is you should think about now the prior is on the mean. And if you want to have the mean to behave as the same as the population, like, so what they're doing is we have a bunch of data over here. In some sense that it's from the same population. So I have y1 to yn to be a bunch of data over there. And then I know that they're following this particular normal distribution. That's my data model. And then now I want to come up with equivalent mean from the population, or from the sample, sorry. So in that case, I should think about central limit theorem. I should think about what the mean, what the variance of the mean it should be. And then the sampling distribution is a normal, and because even before, so think about this, we start with theta sigma squared, mu zero, and tau zero squared. We start with that. So those are given. But now we're just trying to link this sigma square and the tau zero square. And if you think about kappa zero to be the prior sample size, then sigma square should be tau zero squared times kappa zero, or tau zero squared should be sigma squared divided by kappa zero. And that kappa zero is the prior sample size, and that is from central limit theorem. Make sense now? Okay. All right. Yeah, I think that's all I prepared. I printed out all of the solutions, for the homework with me. So if you have any questions, I'm happy to answer them as well. And, or any comments here and there. What are, like, I assume most of you have read through the solutions I provided. So hopefully, there are multiple ways to answer one question. So it's not like fixed that you have to go through the way that I provided. But hopefully those make sense to you. And if not, I think now is the chance that you can ask questions or anything about the material, like is just preparing for it, the midterm. Yes. Okay, so it's the Glenshore example. Okay, so it's so Glenshore, say it wrong. Glenshore. So it's having two parameters, A and theta, and they actually ask you that, assume that you know what A is. So it's a one parameter model, only theta is random. Okay, so they give you the density. And this density is about the data. Okay, right. So now the task, and y over here, and the tasks over here is how to find a class of conjugate prior densities for theta. Okay, so let's, okay, so we know that in order to derive posterior, the general approach that we take is most of the time you're given what the prior is, you're given what the likelihood is, and then you're asked to derive the posterior. And the strategy, like the procedure is you put everything together and try to recognize like what are the terms related to theta, right? So if now we try to come up, say, now we try to come up a class of conjugate prior for theta, that means whatever that this should follow, whatever like the term, like all of the terms that are related to theta in the prior, they should have the same form, like theta is related in the likelihood, because otherwise in the end you cannot combine them to recognize it to be something of the same class. So let's look at what thetas are, how theta are related in the likelihood itself. So you see that here theta is to the power of 2a, and here it's theta, it's in the exponent and negative something times sigma theta squared, right? So this gives out some hint of if in the prior, if we have, so in the solution that I provided, I was writing a very generic term over here, theta raised to some power, and then in the exponent, negative c, which is a constant, and then theta squared. If we have in the kernel of theta something like this, we'll be able to combine this with, so sorry, we'll be able to combine this with this, and then also combine this with this, right? Yeah. So so the solution that I provided was this. So then if you have a prior like this, then your posterior will be, if you have strictly like theta raised to b over here, then you're going to have theta raised to 2a plus b, and then in the exponent, negative y squared plus c, and then theta squared, right? And then if I define this is my prior distribution, then with parameters, the hyperparameters b and c, then my new posterior will be the same class, but with 2a plus b and y squared plus c as the hyperparameters. Okay, so this, I just want to also, like, that's a great question, because another note I should also make here as well. Some of you were asking later, well, how am I supposed to know that this is a proper density? I don't know if this is going to integrate to 1. How am I going to deal with the normalizing constant in front? So So for the homework, if you have done this, like this is good enough, but the question is definitely legitimate. So what another set of solution that we can have is, in fact, Galen-Shor itself, it's a conjugate class. Okay, so if you look at, yeah, so let's look at the density closely again. So here is theta raised to some power, and then in here, it's y squared, like in the exponent, it's negative sigma square, a theta square, and then y square, right? So if you have, let's do, I don't know, B and C, okay? So if you have your prior to be this, you will notice that your prior will be, okay, 2 over gamma. So I'm rewriting this, rewriting the Galen-Shor, but now I'm writing it for Galen-Shor BC, and theta follows Galen-Shor BC. Okay, so that means I will have gamma B, and then here is, okay, be careful. Here is C raised to the power of 2B, and then theta raised to the power of 2B minus 1. And then in the exponent, it's gonna be negative, what is it? C theta square, what is the y square over here? C square? C square, right? Okay, yeah, Right, so if I put a Galen-Shor BC as the prior, my prior density P theta would be in this form. Right? There is some constant, like this is a constant, this is related to theta, and this is related to theta, so we cannot throw it away, right? And then if you combine with the data over here, oh, sorry, data over here, oh, the data over here, sorry, up here, then you will know that you're gonna come up with theta given y. Let's just write proportional. So in the prior, is theta to the power of 2b minus 1, and in the data, it's theta to the 2a. So it's going to be 2a plus 2b minus 1, right? And the exponent is going to be c squared plus y squared, and then theta squared. And that will work just as fine, because this will be another Galen-Shor. Okay, so both of the answers are correct. I think because I posted this approach on Moodle, so that's how, like, because people asked me before, so I posted that, and then that's what I put in the particular solutions that I provided. But Galen-Shor itself will work as well, and in some sense, it's probably a better choice because we know that Galen-Shor is a proper distribution that's going to be integrable to 1, while whatever we came up over here is we don't know, and then it's going to be some calculus exercise over there to make sure how you can get the normalizing constant, but don't worry too much about that over here. Okay, does that, oh sorry, like Elisa, is that okay?
Yeah. The actual test itself, if we approach a problem like this, we will find the posterior from given the prior, maybe you determine the prior. Is it fine to leave it as proportional?
Yeah. Okay, so this question is, okay, so 3.9 is, I tell you what the likelihood is, and I ask you to come up with a class of prior, like conjugate prior, right? So in that case, I was saying, because for me, what I need to make sure that you know how to do is how to say, come up with like some kind of class, and then in terms of whether you're gonna have like the correct normalizing constant or not, I wouldn't worry too much at the moment. So if you do something, I mean, that's pretty much like the solution that provided. So that will be like the level I'm asking for. Yeah. But for example, if you're given a, like a prior, like I tell you what the prior is, I tell you what the data model is, then you can still work with the proportional, especially if I tell you that's conjugate, then you don't have to worry about the normalizing constants. Yeah. Yes.
It's a bit late, but I know the comma zero I mentioned before. So even forming our prior belief, we use the number of observations we had in previous data, but all the observations results.
Yes. Okay. So that was about the normal, right? And we were talking about tau 0 to be sigma 0 over kappa 0. Okay. And then it was the prior is this. Yeah, so there are really like two things over here about how we are thinking about this prior distribution, okay? So first of all, we were doing a data model to be normal. So if you step back and think about what we're doing exactly, you'll realize that the data model is a normal, and we assume that the mean is theta, variance is known as sigma squared. And now, because I want to make inference about theta, I start, because it's conjugate, then I start with class, which is normal again. I start with the prior to be another normal, and then I try to do the derivation and realize it's conjugate, okay? So just step back, thinking about what we're doing over here. You're trying to make inference about the mean of a normal distribution, okay? And what you're doing is you put another normal there. So what you're saying is, okay, I believe the mean of the normal is another normal distribution. And I believe that it centers at mu0 with variance tau 0 squared, okay? So think about how you can play with different priors. So for example, like the mid-wing length example over there, they told you what they did, and then they seem to make sense. A lot of times, if you're actually given a particular like setup and then a set of data point and ask you to say perform this particular analysis, you actually need to be very careful, and then maybe a bunch of trial and error in order to decide what is the normal prior that you're putting on. Okay, so mu0 is your belief that the mean should be center at, and tau 0 squared is the variance that you believe your mean should be like half in terms of the spread, okay? So for example, if I think my mean is very variable, then I will put a really large tau 0 square, right? If I think it's not that variable, then I'm gonna put a smaller one, okay? So with kappa 0 over here, so a lot of times we're trying to, let's see. Here we're trying to imagine it to be a prior sample size, meaning that you imagine that you can generate a bunch of prior observations to represent your belief. So here, I think, to me, to be honest, it's more for the pedagogy reason that you start with a kappa 0, so you can start like feeling, okay, actually, if you think of this as the prior sample size, you can, so if you think about the prior sample size, the larger the sample size, you can think of it as more confident that you have about your prior, okay? So aside from what we talked about, like how to understand this particular normal prior over here, a different question is how much confidence I do have in this particular prior, okay? So for this one parameter normal case, I would like everybody to think of this as assume kappa 0 is the prior size, then the larger the prior size, the more confident that you have that you're gonna put in your prior. And then if you are not that very confident, then you're gonna choose a very small kappa 0, which represents a small sample size. So think about sample size. There's multiple sample size over here, okay? The data, which is n, right? And then for the normal, which is in the prior, if we define it in the way that we define it, it's gonna be kappa 0, okay? And we know that the posterior mean is a weighted average of the prior mean and the sample mean, right? So if you think about this particular setup, you'll realize like the change of kappa 0 gonna really affect the mean of the posterior. So if kappa 0 is large, then this ratio gonna be large, then the contribution of the prior mean gonna be larger, right? Because n is fixed, I only have that amount of data, right? So kappa 0 is really like a parameter here that can help you to like show your confidence in some way. So I would say, so first of all, like the question, like the earlier question I was trying to answer is how come you set up this way? What is divided by kappa 0? And that's because of central limit theorem, because this is the variance of the mean, and this is the variance of the data. And if you're curious about the variance of mean from central limit theorem, it is the sample mean, or like the, sorry, not sample mean, the population variance divided by the sample size. And if you think about kappa 0 as the sample size, then this will make sense. Okay, so that's how it is set up. And then in order to think about how you're going to choose your kappa 0, then that's really about your prior belief, how strongly you believe in that. So it's really two separate things. First of all, it's a normal prior, and you can play with mu0, you can play with tau 0 square to show what the distribution that you think the prior would be. But then there's always another layer over here, is how confident you are in your prior. And in this particular case, kappa 0 is the parameter that you can tune. Okay, actually, I mean, this, so if you guys can turn to the page, because we talked about even for the beta binomial case, remember? We talked about the posterior mean is the weighted average of the sample mean and the prior mean. So you also see some, let's see, so it's in chapter 3, but I'm trying to find the notation. Oh, it's in, let's see. Yeah, it's in page 38. If you look at it, like combine, like at the bottom, combining information. So over there, you start, so that particular section is talking about, oh, sorry, 39, that's even better. 39 in the middle. They show you how the posterior mean of the beta binomial model, the posterior mean of the beta, which is, of the theta, which is the beta distribution, it's gonna be the weighted average of the prior expectation and the data average, right? So over there, if you look at it, the prior expectation, let me write over here. So they have the expectation of theta given y to be a plus b divided by a plus b plus n times prior expectation, so prior, right, plus n over a plus b plus n times data expectation, right? Yeah, so these are the weights. We actually talked about it before, but back then, I don't want to confuse people in terms of how to think of things in terms of prior size. But if you read the textbook, you realize that they also talk about a plus b as a prior sample size for the beta binomial model. So now if you look at the form, that makes sense, right? A plus b, because that is the contribution of the prior expectation that you can have. And then n is the contribution that the data expectation can have. I mean, all of the contributions are on the posterior mean. So realize if you think about a plus b as a prior sample size, that also makes sense in terms of this setup, right? So if we go back to think about this beta binomial particular density, so you think about if this is going to be beta AB, then the prior gonna, forgot the particular, gonna, oh, theta raised to a minus 1, and then 1 minus theta raised to b minus 1, right? So over here, this is, okay, so again, twofold. What is the data, what is the prior like? And then how confident I am. Right? So choosing A and B can give me different shapes of the beta, right? And that's something that we consider because we want to present our belief through the prior, right? But also A and B itself, the values of A and B, you might be able to tweak it in order to show like a stronger belief or like a very weak belief. So A and B add up together, obviously in this case, will be a prior sample size. So just to give you a note, let me see, like a way to think of this. So the mean of, give me a second. The mean. So for the beta distribution, I think the mean is A over B, is that right? Yeah, oh, sorry, the mean, okay. So the mean for like this beta will be A over A plus B, right? That's just like the mean, for example. I don't remember if I talked about this before, but I kind of remember, maybe it should be in this class, because otherwise I don't know where I talked about this. But here, think about, if I want to fix the mean of my prior, if I want to do it 1/2, okay? I can do it as 5 over 5 plus 5, right? Choosing A equals to 5 and B equals to 5. That gives me 1/2, right? My first choice. A second choice will be, okay, since I just want to fix it to be half, I can also do 100 over 100 plus 100, right? And A and B are both 100, right? So for these two different priors, I represent the same belief in terms of the mean. Both of the means are 1/2, right? But the prior confidence I have is vastly different, right? Because the confidence, if I think about it in terms of A plus B as the prior size, then in this case, A plus B is only 10, while here, A plus B is 200, right? And then if the sample size, like N, if N is really small or like not really large, then if you have a 200 prior size compared to a 10 prior size, it's gonna be vastly different. Okay, so I think starting from now, since we have all of the background and set up all together, let's start to think about, for any prior that we put on, we not only think about what the prior is like, how it's gonna represent our belief, but we should also think about what is the prior sample size. Okay, so in the beta binomial, we have seen it, it's A plus B. In the gamma Poisson, I forgot exactly what it is, but I think like the whatever, like some kind of algebra of the parameters over there gonna represent the prior sample size. And then in the normal, kappa 0 is what we define, but it still makes sense from the central limit theorem. That kappa 0 is considered to be the prior sample size, and then you can play with that to see how you want to show your confidence in some sense. Make sense?
So it doesn't mean that we, by saying kappa 0 is like a prior sample size, that we actually collected a sample from this population previously.
Yeah, okay. Right, okay. It's a good point, because I think, oh yeah, keep going.
Just saying that we choose kappa naught or kappa 0 to be the prior sample size, because that like makes the math work such
yeah,
that
so
interpretation.
Right. So to be honest, I think like for pedagogy reason, that's pretty obvious that if you define kappa 0 to be like that, then the math works out, and then it's still like interpretation wise it makes sense as well. But still, like, but now tied up everything together, I think we are like, we're more comfortable right now to think about how prior sample size is telling us in terms of the confidence that we have, okay? But I think Nick's question is different. So Nick's question, this is again a bigger question over here. So how are we gonna come up with the prior? Okay, so obviously we talked about some easy ways that we thought about, okay, you can try with different things, or you might know from some previous studies that you want to put a prior like that. Okay, so here, the prior sample size for what we are talking about right now, try not to think of it as really trying to generate some data or like from the previous study or whatever to use that as a prior sample size, okay? It's mostly for ways for us to understand how the prior, how we can, so for different models, you can have different prior sample size, the way that is set up. For beta binomial, it's gonna be A plus B, okay? And then for the normal, the one parameter normal, it becomes kappa 0 that we talked about. Okay. Yeah. Anything else? I don't mind ending early. So if no more questions, I will just post the solutions to your homework 3 right now after the class ends, so you can take a look. And again, if you have questions, you can ask me right before the exam, so I can answer those. And Oh, yeah.
So this one should be pretty quick, but in class, we at one point, looking at the beta binomial conjugacy, we took two posteriors, one for theta A condition on one, and one for theta B condition on one, and divided them, and then showed that that in and of itself was also a beta posterior. I don't know, was there sort of, is that, I don't quite understand the intention behind that. Is this something that we should know? Or?
Okay, I just couldn't bring my Dropbox right now. Can you tell me a little bit, like, what exactly is that?
So we took the probability of theta A condition on
Yeah.
y1 to y,
Right.
and the probability of theta B condition on y1 to y, to solve that. And then the conclusion that we came to is that it's theta A over theta B raised to the power of the sum of all yi. Theta 1 minus theta A over 1 minus theta B raised to the power of n minus the sum of all yi, which is basically just, it's to the, it's exactly what we would expect. It's like, I don't know, it's the beta, or so the binomial distribution of the ratio of the two. And then there was some sort of conclusion that I just never really understood.
Okay, so can you tell me which page of the slide is that, really quick, or it's on book? Okay, 35. I mean, my guess is it's actually trying to answer a particular question, but I don't know. Okay, 35, inference, posterior.
Yeah, it's like this big term in the middle. They talk about it as demonstrating sufficient statistics.
Okay. Yeah, it's 35. Yeah, page 35. Inference for exchangeable binary data. Okay, so they have. Oh, okay. Oh, I see. Okay. Okay. So this, if you remember from the first chapter that we talked about something called Bayes factor. If you remember it. Yeah, it's just unfortunate I couldn't bring the Dropbox on this because I think that would be easier if I can show you the slides. So give me just really, maybe let me try it really quick. Why I cannot log on Dropbox. Yeah, because that's related to, so the page 35, when they're talking about that, it's really talking about how, give me a second, sorry. Yeah, somehow I couldn't get it out. Let me try something really quick. Sorry about this. Give me a second. Okay. Let me try. I can get it from Google. Okay, so page 35 is really talking about what if you're doing multiple comparing. So we know what the posterior is for this particular situation is beta binomial, and then it's going to be a beta. So the question here is how you gonna. Okay, I should be able to bring this up. Awesome. Okay. Where's that? Yeah, it's over here. Okay, so in chapter 1 back then, we're looking at, okay, if you can have a partition of the hypothesis, and then which is H1 until HK, and then E is the outcome. Then to compare the hypothesis after the experiment, that's pretty much doing this, right? And then if you try to derive things step by step, so what is this? This is the posterior probability of hypothesis 1, hypothesis I, over the posterior probability of hypothesis J, okay? And if you derive it step by step, you realize that this ratio is the product of two ratios. The first ratio is the ratio of the likelihood of the data given the two hypotheses. And the second ratio over here is the ratio of the prior beliefs, okay? So on page 35, it's just redoing this, but now in terms of the beta binomial setup. So if you read it, so they're not doing like two separate like populations or anything. They're just thinking about two particular theta values, theta A and theta B. And if you do that, like say, so if you read 35 on page 35, you realize they show it, and then there are a lot of terms canceled out. So first of all, the marginal density of the data canceled out, and then like it's really about the ratio of theta A and theta B raised to sum of yi, and then the ratio of 1 minus theta A and 1 minus theta B raised to the power of n minus sum of yi. So you can actually rewrite your ratio of the posterior, but now in terms of theta A given all of the y and theta B given all of the y, I realize, okay, the first term over there, like the first two terms, let me write it over here. Yeah, so if you read the text, like the textbook over there, they write it as theta A given all of the y over. So this is really evaluating which value of the theta is more possible, right? After you see the data, after you apply the model. So you see that it's in terms of theta A over theta B raised to a ratio, raised to the power of sum of yi, and then 1 minus theta A over 1 minus theta B raised to the power of m minus sum of yi, and then the prior ratio, right? So in what we defined before, this will be the base factor. Okay? Don't worry too much about the terminology here, but overall, you see that in order to compare which one is more likely, which value of theta is more likely, you can break it into two parts. Okay, this is the part which is contribution from the prior, and this is the part contribution from the data. Okay, so if you read this, obviously, as long as you know the sum of yi, you know everything about this ratio. Yeah, so this is a sufficient statistic. And unsurprisingly, if you are not comparing statistics, if you are not really trying to compare, like take the ratio, if you just look at the likelihood itself, you can also derive that sum of yi is a sufficient statistic. So I think over there is really just talking about how you can, yeah, it's nothing too complicated over there, but it's just, I actually don't think I talked about this particular part in the lecture, but again, this relates to lecture 1 when we talk about base factor, et cetera, et cetera. So overall, try to see the motivation of doing this. Okay? We really have multiple hypotheses about the parameter, and then we want to see how likely how likely the posterior probability of each of the hypotheses will be after we see the data. So for the beta binomial case, this is what you're going to do. Okay, and then you derive and you realize, okay, it's the contribution from the ratio of the prior, and then the contribution from ratio of the data. And in particular, the data is the form of sum of yi, which is not surprising because for the binomial model, sum of the yi is the only thing that matters pretty much. Because the number of successes. Okay? Mm-hmm. Yeah. Anything else? Okay. Right, so, okay, so two kinds of, okay, intervals. We talk about two kinds. So central, what is it, central, or like quantile based, sorry, I shouldn't write central. Okay, so quantile-based intervals, based on what we have seen so far, because we're working with conjugacy, so you know exactly what the posterior distribution it would be. So if it's beta, we use like Q beta. If it's gamma, we use Q gamma. And then if it's normal, we use Q normal, right? And then you fit in whatever you need for all of this, maybe multiple over there. So those is quantile-based intervals. And then because in Bayesian analysis, we assume that the parameter is random. So if you try to produce, say, a 95% quantile-based, I want to have the 95% central quantile-based. So I would do like, say, for Q beta, I will fit in things like, what is it, C 0.025, 0.0975, and then the A and B, and then try to get a confidence, like central 95% confidence interval, because I'm trying to get the cutoff points. So this is cutoff 1, this is cutoff 2, and I'm using the quantile function of beta, so I know I can get the value of the cutoff point on the left, which gives you 2.5% to the left, and then here gives you the 97.5% on the left. But there's two cutoff points. If you take this as the interval, that gives you a 95% quantile-based interval. Okay, and HPD is the highest posterior density interval, is what we say that people actually would prefer to do in the Bayesian analysis, and we talked about how you can like understand how HPD is getting in, how that is obtained, right? So we're talking about, say, you have a density like this, central. So this, I mean, it's a different color. So for quantile based, you're pretty much just, all right, I'm gonna cut off this 5% over here, 2.5% over here, 2.5% over here, and then I come up with that, right? So for HPD, it's different, because what we want is actually to return the most likely posterior, like most likely values, which has the highest posterior density, right? So the way that we came up with this, intuitively, is you're gonna have like a cutoff, like a line over there, and just keep moving down, because this is the density, so you know that everything above the line you're gonna have probability larger than the ones below it. So you're gonna keep going until you hit, say, suppose this case, let me use a different color. All of this inside here is 95%. Okay, so highest, yeah, HPD interval is trying to return you the first 95% most likely values of the data, of the parameter. Okay, so in R, I told you that you should use a, what is it, the library called CODA. I think I had some sample code in the lecture. You should use the CODA library, and then you're gonna turn, say, okay, now suppose this is theta. Suppose I have theta posterior stored as something, and then I will turn it into MC object. So this is just some formality over here. You're gonna do as.mc parenthesis whatever you have named it before, like the vector of all of the samples that you have. And then once you turn it into MC project object, then I think you just get, I forgot exactly the notation, but it's, I mean, the name of the function, but it's something related to HPD, and you just fit in what the theta post, and it's gonna return you 95% HPD interval. Okay, so pretty much, I mean, depends on the question. If they ask you just to get a quantile based, then you can just use the Q beta, Q gamma, Q normal here and there. But if it's doing a HPD interval, then you can use the coda library. Okay? But of course, you need to make sure that you understand the differences between these two. And then I can only say most cases, I think in Bayesian analysis, people like to return this one because you actually have the facility to do that. And that makes more sense as well, because I want to return the most likely set of values that theta can have. Does that make sense? Okay. Anything else? Or anything else I should post on Moodle? In addition to, I would post the solutions to homework 3. But other than that, I don't know what else it's missing. I think most of the material. So yeah, if you try to review, make sure that you go like on Moodle, like try to get the material like section by section. Most of the time, each section gonna have like the lecture slides, some R demonstration code, and then what else? Some discussion topics over there if you've seen any of them, and then yeah, mostly some R code, and then sometimes I have labs here and there. So for lab 1, I provide both the lab and then the solution, so you can read through. For lab 2, I didn't write out the solution, but I posted the R code to do that, which should be straightforward. So hopefully that's sufficient. And yeah, so anything, if you like extra questions, I guess it's probably easier if you ask me right before exam, because I don't know how often I'm gonna check my email until then. Okay. All right. Good luck.